Hello, everybody. How are you, my calculus class? Kevin is here, teaching a little bit about differential equations today. As I mentioned in a previous video, the College Board has come out with some new guidelines for this year's AP test only, and they've taken out a couple sections. The good news is we covered all but four. The bad news is those four sections are not even in the book you have. Well, they're not in the first volume of the book. Notice here it says Volume 2. We're in Volume 2 of the book. I'll send you a link to it, although I'm sure you don't need me to, but I'll do it anyway to make sure I'm doing my job. So it's actually the Volume 2 part of the book, Section 4.1. Seems weird to go all the way to Chapter 4, but if you go to Volume 2, you look at the first three chapters are basically a recap of what we did. So we're going to talk about differential equations. Now, differential equations are called by a short name for differential equations is DiffEq. It's a much cooler name. And that's what we call the class when we take an entire class of differential equations, which basically means taking derivatives and seeing what they do. So, and that's what a differential equation is. A differential equation is simply an equation that relates a function to one or more of its derivatives. Let me give you an example. This is a differential equation. You've seen that equation before, y prime equals 2x. In fact, you could probably solve that differential equation, which means what does y equal? Yes, y equals x squared plus c. We'll be solving differential equations a little bit later because, of course, they're going to get more complicated. But basically, this is what a differential equation is. Here's another differential equation. That's a differential equation. It's got y. I know y is not explicitly stated in there, but you have a first derivative and second derivative of y. This could be a differential equation. Oh yeah, y prime minus xy equals 4x minus 2y cubed. That is a differential equation that relates its y to one of its derivatives, y prime. Now you might be thinking, wait a minute, that doesn't relate y to y prime. Well, y is there. Because if you took the antiderivative, if you found the solution of that, you would get y equals. And that's the point. Is it possible to solve this differential equation? Can we set that, say, y equals something? Maybe or maybe not. That's what we're going to learn a little bit later. But for right now, we're just going to learn what the differential equations are and how we can verify that a solution is true. So before we do that, we'll talk about an order of differential equation. That's called a first order differential equation. Can you guess why? You probably can, but I'll tell you, what about this one? That's called a second order. Guess what this is? Can you see why? Just like when you did polynomials and you did their powers, that was, their degree. If you've got yourself a first degree, it's because it's y prime. There's one derivative. This goes up to a second derivative, second order. That's a third derivative, third order. Here's what we're going to start with. We're being given a differential equation, y prime equals x squared. The question is this a solution to the differential equation? Basically what you mean is, if I took this derivative, would it fit that equation? And I think this one is pretty obvious, because x cubed over 3, the derivative would be 3x squared, and that over 3 is just a constant, so y prime is x squared. So if I plug in the value here to technically solve or substitute x squared in for y prime, and you come up with a true statement. It's a true statement, so you can say that y equals x cubed over 3 is a solution. All right, that's the basic. So we'll throw a couple more examples out there and make sure it all works out fine. Now we have a second order differential equation. It's y double prime minus y equals 0. Well, that's y. Now we got to find y double prime. Ah, e to the x. We like that one because the derivative of e to the x is e to the x. So nothing's going to change there. Y prime is ce to the x. Y double prime, the second derivative, is the same. This derivative will be the same for infinity. So it's pretty boring to never ever change. Y double prime we know equals ce to the x minus y, which we know equals ce to the x. And that's a true statement because ce to the x minus ce to the x does indeed equal 0. That's true. So y equals ce to the x is a solution. All right, not so bad. Let's take a look at this one. It might have seemed that this one was pretty easy to see, especially now you know a little bit more. Just take that derivative, it happens to equal that. I mean, these are statements that are true compared to each other. This is the solution to this equation. This one's not as easy to see. Is this going to be the solution to this equation? Well, so there's a little work to do, but it's really all the same thing. So c is a constant, so cx squared, the derivative of cx squared would be 2 times cx minus 3. Now I plug this information into here. So I'm going to write this over here, just get some more room. X times y prime. Well, y prime is 2cx minus 3. Minus 3x minus 2 times y. Now don't just put y. We know that y equals cx squared minus 3x. So substitute all these values in for this. And now we see if it's true. So I'll distribute that through. Be careful. Don't do what I do and sometimes forget the old distributing a negative through. But here you can see that 2c x squared minus 2c x squared definitely becomes 0. And that negative 3x minus 3x plus 6x also becomes 0. So 0, there we go. 0 plus 0 equals 0, which is a true statement. So therefore, that is a solution. Okay? One more. Now I can't make them all solutions, so I made one definitely is not a solution. And you might be able to tell, you'll be able to tell quickly if it's not going to work. So y equals 5 natural log of x. Does the fourth derivative minus 16y equal 0? All right. Well, it's 5 natural log of x. So let's find the first derivative. There's your constant. The derivative of natural log of x is 1 over x. Now I'm going to write it this way because it's going to be easier to take the rest of the derivatives. So the second derivative, negative 5 x to the negative 2. Third derivative, 10 x to the negative 3. And the fourth derivative, negative 30 x to the negative 4. Okay. So there's my fourth derivative. There's my original equation. Is this going to be true? Y to the fourth is negative 30 x to the negative 4 minus 16 times 5 natural log of x going to equal 0? No. No, that's not true. So this is not a solution. Okay? Couldn't make them all work. Had to show you that they don't always work out. So that's how you verify if solutions to differential equations are correct. All couple more problems now. Let's just find a general solution. Let's just take a differential equation and find the solution if we can. You're going to find out some are easy and some are hard and some are impossible. So we won't talk about the impossible ones. That's for really higher order mathematics to talk about. We're worried about just introductory levels to differential equations. So what we have here, y prime equals e to the x minus y prime equals e to the x plus sine x plus 1 over x plus 3x squared. Well, guess what? Basically, aren't you just taking the antiderivative of everything? What's the antiderivative of y prime? Well, it's y. I mean, so technically we're doing this. Then what's the antiderivative of all of this? Well, antiderivative of e to the x, e to the x. Antiderivative of sine, derivative of sine is cosine, so antiderivative is negative cosine. Antiderivative of 1 over x, natural log, and that's going to be x cubed. Pretty easy to verify. Does this derivative equal that original equation? So y prime would equal e to the x plus sine of x plus 1 over x plus 3x squared. That is a general solution to the differential equation, but I forgot something. Plus some constant at the end. Hence the word general solution. It's not specific. It's really an infinite number of answers because that C could be an infinite possibilities. But that is your general solution to this equation. All right? Same thing here. Aren't I really just taking the integral of these? Hopefully it might be a little rusty on this one, but how do I take the antiderivative of that? Now, I'm not trying to make them too challenging at first. If you think about it, would this be correct? If you take the derivative of this, don't you get derivative of y is y prime? The derivative of e to the x cubed is e to the x cubed times, I'm going to fix that, sorry about that. That just drove me crazy. All right, the derivative of e to the x cubed is e to the x cubed times the derivative of the exponent, because that's chain rule, is 3x squared. The derivative of c is 0. So isn't this what I have up here? Just written in a different order. Now, if you remember, that was what we call the substitution method of finding derivatives, and you've done that. So we will be using substitution method to find the solutions to differential equations also, if applicable. And in this case, it is. So this is the general solution to that differential equation. Now, if you don't remember use substitution or the substitution method, don't worry, we'll go over it again. This is just an example. Now we're being asked to find a particular solution, which means no general anymore. We're given the general solution, which is really nice. It tells us that, because that saves us a lot of work. So if this is our differential equation, and it's passing through the point 0, 12, how do I find the particular solution? Well, I just throw the general solution and throw it through that point. Because remember, a general solution, you basically have the graph, but the graph, we don't know how far it shifts up or down. That's the C value. Okay. Well, we're going to lock it in at 0, 12. So let's lock that in and see what we got. So the y value is 12. And 0 cubed is 0. So e to the 0 is 1. We have that. So our particular solution is 12e to the x cubed. Now, it's not a bad idea to verify that. So let's just verify that to make sure. So we'll put it into this differential equation. So I know that y is this, which means that y prime would equal 12e to the x cubed, because e to the x cubed is e to the x cubed, times the derivative of the exponent, which would be 3x squared. So y prime would actually equal 36x squared times e to the x cubed. All right. And we know what y equals. We know what y prime equals. So let's plug it in. So y prime, which is 36 x squared times e to the x cubed equals 3x squared times y. And y is 12e to the x cubed. Well, take a look at it. What do you think? Looks pretty solid to me. 36x squared e to the x squared. If I multiply 12 times 3, I get 36. Let's write it out. 36x squared times e to the x cubed equals 12 times 3 is 36 x squared times e to the x cubed. That's a true statement, so we have verified that that is the particular solution. Now, did you really need to do all this? You did not need to do all that, but I wanted to show you that the answer worked. Okay. If I'm telling you this is a solution, you don't ever have to really do this, but we did in this case. All right, one more. We're finding a particular solution to this one, but we're not given what the general solution is, so we really have to figure it out. Now, it's a pretty easy one. So just remember dy over dt really equals y prime. It's just we're verifying that it's with respect to the variable of t. That's going to become actually quite important later on. So basically, what would the antiderivative of dy over dt be? That would just be y. What's the antiderivative of 2t? Well, it's really t squared plus some constant. Now, what is that constant? Well, we're going to look back up here because we were given some information. That information is that. Now, I know in physics you use y sub I. I think we've talked about that before, but initial value, we always use numbers in calculus. I don't know why it differs from physics. We just do. So y of 0 equals 10. So if I plug that information right into that, here's what I end up with. A couple of arrows there, you like them? So the y value equals 10. The t value equals 0. So the c value is 10. So our equation is this. So it's the parabola y equals t squared plus 10. So I threw a couple extra questions in for you. At what time does y increase to 100? Well, let's take our solution to our differential equation and let's set it equal to 100. Okay. Solve it. Subtract 10 from both sides. There we go. Square root. Now, I know it's plus or minus, but we're talking about time. We're not going backwards. We're not going to negative time. So we're just going to say t equals the square root of 90. And I believe that was seconds. Was that seconds? I don't know what to do. It didn't really say. So what time? Time is the square root of 90. Now, I know some of you guys are grabbing your calculators because you got to figure out the square root of 90, but there it is. Okay, it's 9 point something. Let me guess, 9.5, because 81 and 100 right in the middle. Anyway, that's my guess, but we don't care. It's the square root of 90. Now, the other question was, well, what happens when it equals 1? Well, I think you can already figure out what's going to happen here. It will never equal 1. Okay, because, whoa, what happened with my e? Oh, no, I got to do that again. All right. It will never get to 1. And if you think about it, t squared plus 10 is a parabola. Starts at 10, goes up forever. It's never going to get back down here to 1. So that's how you do differential equations. We'll be having 3 more lessons. One's going to be on slope fields and direction fields, which are graphical forms of differential equations before we solve for them. The next section will be solving separable differential equations. So we will actually be solving the differential equations. And our third and final topic that we'll study is growth and decay, which you know because you've worked with growth and decay. You've worked with the formula for growth and decay. So if like P equals E to the RT rings a bell, that's exponential growth and decay, and we're going to actually derive where that came from and use it in situations. I hope you enjoyed my lesson. I mean, I enjoyed telling you about maths, as I always do. It's too bad we can't have our dialogue, and I'm sorry I couldn't make any jokes. But, I made mistakes, which is, always good too. I will contact you guys later about the next topic. I plan to put the next topic up within 2 days. So every other day have the new topic up and give you guys some problems to work on. What I'd like you to do is, just like before, know how to do these. If you can do those problems, you're all set. Once we get through these, I'll send you guys a review and we'll take a test on it. The test will be just like the Chapter 5 test. I'll just send it to you. You do it, you send it back. So we'll be done. Whether or not we meet anytime again this year, or however that's going to happen, we'll be done with this within 2 weeks. And then we'll have all that time left to study for the AP test if that's what you're taking, or to review, to put all the concepts together if you're not taking it. But whatever we're doing after that will be important for everybody. Useful, I should say, to everybody. So until then, enjoy yourselves. Don't get into too much trouble at home. And just do the best you can. Talk to you later.